students, we are discussing your third chapter, that is electrochemistry. In the earlier class we have discussed how to measure the standard electrode potential. To measure the standard electrode potential, the concentration of the electrolyte must be taken in the unity, but it is not necessary to be unity the concentration of electrolyte always. We can determine the electrode potential at any concentration also. So Nernst established a relation or equation to find out the electrode potential at any concentration, and today we will discuss the Nernst equation, its application. So you see here the Nernst equation, that Nernst showed that for the electrode reaction Mn plus Ne gives M solid. That means here this is a reduction electrode reaction. So here the metal cation having the charge N plus absorb the N number of electrons and thereby it becomes the metal solid. Now for this reduction reaction, the electrode potential at any concentration can be represented by, that is, electrode potential for this electrode for this reduction reaction, that is E standard electrode minus RT NF ln of concentration of M by concentration of Mn plus. So this is the concentration of, means this is the concentration of the solid metal, and the concentration of the solid metal that is taken as unity. So that's why this will be electrode potential for the electrode, that is equal to standard electrode potential for the electrode minus RT by NF ln of 1 by concentration of Mn plus. So here R is a gas constant that already we know, its value is 8.314 joule per Kelvin per mole, and F is the Faraday's constant, its value is 96487 coulomb per mole. So what is Faraday's constant? That is the charge of 1 mole of electron. So we know the charge of 1 electron, that is 1.6 into 10 to the power minus 19. Now if we multiply it by 6.02 into 10 to the power 23, then this will be the charge of 1 mole of electron, and that exactly comes into this 96487 coulomb per mole, and roughly for our calculation purpose we can take it as 96500 coulomb per mole. And temperature, that is T, that is the temperature in Kelvin scale, and Mn plus, that is the concentration of Mn plus, that is the concentration of the species Mn plus. So this way we get the Nernst equation, that is called the Nernst equation. That means the electrode potential of an electrode at any concentration, that is equal to the standard electrode potential minus RT by NF ln of 1 by concentration of Mn plus. So now if we take the Daniell cell as an example, for Daniell cell, so Daniell cell, that is represented it like that zinc, that is oxidized to zinc 2 plus separated by a salt bridge, copper 2 plus, that is reduced to copper. So this is the representation of a Daniell cell. Here the oxidation of zinc is taking place and reduction of the copper ion is taking place. So for this Daniell cell, the electrode potential for any given concentration of copper 2 plus and zinc 2 plus, we can write the Nernst equation like that. So for cathode, so in the cathode the reduction of the copper 2 plus is taking place. So for the cathode, the electrode potential for the cathode, that is equal to standard electrode potential for the copper electrode minus RT by 2F ln of 1 by concentration of copper 2 plus. Similarly in the anode, that is that electrode is the zinc electrode. So for the reduction of that zinc ion to that of the zinc, so electrode potential for the zinc electrode, that will be equal to the standard electrode of the zinc electrode minus RT by 2F ln of 1 by concentration of zinc 2 plus. So now you see here that at anode actually the oxidation reduction is taking place, but we are to consider the reduction reaction here. So that's why we are writing here zinc 2 plus, that is reduced to zinc. So now this way, for the Daniell cell, this is the electrode potential for the cathode and this is the electrode potential for the anode at any concentration. So thereby the cell potential, that E cell, that will be equal to electrode potential for the cathode minus electrode potential for the anode. So this is the cathode, this is for anode. So this electrode potential for the cathode, that will be equal to E standard for the cathode minus RT by 2F ln of 1 by Cu2 plus. Similarly, electrode potential for the anode, that will be again E standard anode minus RT by twice F ln of 1 by concentration of zinc 2 plus. So since one minus sign is there before that, so this will be minus and that part minus this will be your plus. So now E standard cathode minus E standard anode, so that is E standard cell. If you take the common minus RT by 2F here, then that will be ln 1 by copper 2 plus. Here it is a plus, but before that minus is there, so minus ln of 1 by zinc 2 plus, concentration of zinc 2 plus. So now this will be equal to standard cell minus RT by 2F ln of, so here that ln of A minus ln of B, that is ln of A by B. So that means ln of 1 by concentration of copper 2 plus minus ln of 1 by concentration of zinc 2 plus, that will be equal to ln of this divided by this. That means that zinc will go up, so that will be ln of concentration of zinc 2 plus by concentration of copper 2 plus. So thereby it will be E standard cell minus RT by 2F ln, if you convert to that of the log, that means ln is the natural logarithm, log means that is the 10 base logarithm. So then we have to multiply it by 2.303. So ln we can convert to that of the log, so then we have to multiply it by 2.303. So that's why this RT by 2F ln we convert to that of the log, so 2.303 log of concentration of zinc 2 plus divided by concentration of copper 2 plus. So that value, if you put that value of R, value of T, value of F, so that values are already known. T means that is a room temperature. If you consider and multiplied by 2.303, that ultimately come to as 0.059. So here 2, that is the value of N. So if you see the cell reaction of the Daniell cell, then 2 moles of electron is transferred there. So that's why this is the 2. So that will be equal to now that E cell equal to E standard cell minus 0.059 by 2 log of concentration of zinc 2 plus by concentration of copper 2 plus. So this is the Nernst equation for the Daniell cell. So here you remember that here that E cell is equal to E standard cell minus 0.059 by 2. 2 is the number of mole of electron transferred in the cell reaction, log of here the concentration of the ion in the oxidation half divided by concentration of the ion in the reduction half. So that part we have to remember. Similarly for the cell, if we take another cell, so this is the representation of a cell. This is here the oxidation of the nickel is taking place, nickel to that of the nickel 2 plus, and reduction of silver to that of the silver is taking place. So now for this cell, the cell reaction is here the nickel, that is nickel, it will react with that of the silver plus. So nickel, that is oxidized to nickel 2 plus, and silver plus, that is reduced to silver. So for this cell reaction, the Nernst equation can be written as now. Similarly that E cell, that is equal to E standard cell minus RT by F. So here the number of electron involved is the 2 mole of electron, the nickel 2 plus. So here that means the nickel goes to that of the nickel 2 plus by releasing the 2 moles of electron. Similarly here the silver plus, it goes to that of the silver by taking the 1 mole of electron, since it will release the 2 mole of electron. So we have to take here the 2 silver ion and then 2 silver atom will be deposited there. So this is the cell reaction. Here 2 mole of electron is transferred. So that's why that N equal to 2. So the Nernst equation will be equal to that E cell is equal to E standard cell minus RT by twice ln of concentration of the ion in the oxidation half, that is the nickel, divided by concentration of the ion in the reduction half, that is the silver. Now since here that in the balance cell reaction the 2 is here as a stoichiometric coefficient, that will raise as a power. Already we have seen this in that of the equilibrium chapter also, that if any equilibrium any stoichiometric coefficient is there, then that will raise as a power of the concentration of that species. So here the 2 is there before the silver ion, so that will raise as a power. So this is the Nernst equation for this cell. So this way we can generalize that for a general electrochemical reaction of the type A moles of A plus B moles of B gives C moles of C plus D moles of D, where n mole of electron is transferred during this reaction, then the Nernst equation can be written as E cell is equal to E standard cell minus RT by NF ln of Q. Q is the reaction coefficient. So that is equal to what now? From this reaction you see that Q will be equal to that concentration of C raise its stoichiometric coefficient small c as a power into concentration of D raise stoichiometric coefficient small d as a power. That means that that Q reaction coefficient is equal to reaction coefficient, that is equal to the ratio of product of the concentration of the product raised its stoichiometric coefficient as a power by product of the concentration of the reactant raised its stoichiometric coefficient as a power. That means that Q will be equal to concentration of C to the power C into concentration of D to the power D divided by concentration of A to the power A divided by into concentration of B to the power B. So that will be the value of the Q. That means the Nernst equation we can write it like that: E standard cell minus RT by NF ln of this. So this is about the